another module in this massive open online course on Bayesian MMSE estimation for wireless communications, alright. So, previously in the previous modules we have completed the analysis of LMMSE or MMSE estimation for multi-antenna wireless channels. Let us now proceed to look at the corresponding estimation, that is LMMSE and MMSE estimation for MIMO channels. So, what we are going to do starting today is look at MIMO channel estimation, where MIMO stands for multiple input multiple output. So, what we want to do is we want to start looking at the concept or the framework of MIMO channel estimation, correct, where MIMO stands for multiple input MIMO stands for a multiple input multiple output wireless communication system, and what it means basically is that you have multiple antennas as the transmitter and all as well as multiple antennas at the receiver. Previously we have considered multiple antennas only at the transmitter, right, in the downlink wireless channel. Now we are saying we have multiple antennas both at the transmitter and also the receiver. For instance, if you look at a downlink channel, we have multiple antennas both the transmitter, that is the base station, and also the mobile device, which is the receiver, alright. So, multiple input multiple output. So, I can draw a simple scenario depicting multiple input multiple output wireless communication as follows. So, let us say this is my base station. Previously we considered the base station has multiple antennas and that remains same as before. So, I still have multiple antennas at the base station, but now in addition my device also has multiple antennas. So, if I have a mobile device, I also consider multiple antennas at the mobile device. Okay. So, this is my base station. Which has your multiple antennas or also this is becomes your multiple input, because these are the inputs to the channel, and this is the mobile device, and this also has multiple antennas. So, you have multiple antennas at the transmitter and multiple antennas at the receiver, and therefore, what you have now is basically a full fledged MIMO channel. So, what you have now is basically a multiple input. This is a multiple input multiple output, that is basically a MIMO channel. So, MIMO stands for multiple input multiple output, with the multiple inputs mean you have multiple transmit antennas, multiple outputs you mean you have multiple receive antennas, right, and we have illustrated this for the downlink wireless communication scenario, where you have a base station which have multiple transmit antennas and the mobile device which has multiple receive antennas. Okay. And schematically this can be represented as, let me just draw a schematic diagram. Schematically, this can be represented as, let us say you have a transmitter this is your Tx, that is your transmitter, and you have your Rx, that is the receiver. So, I have transmitter, I have the receiver, I have multiple antennas at the transmitter, I have multiple antennas at the receiver, okay. And in between these, naturally what I have is the MIMO channel. And look at this, I have a path between every transmit receive antenna, I have a path between every transmit receive antenna pair, right. Between every transmit antenna and every receive antenna, I have a channel, correct. So, I have a path. So, if I have m transmit antennas and r receive antennas, I am going to have total of a collection of m times r channels, okay. So, let us say I have m transmit antennas similar to before, and I have R receive antennas. I have total of product of m cross r, m times r channels, possible paths or possible links where the signal can propagate from the transmitter to the receiver. Okay. So, let us consider the symbols transmitted on these m transmit antennas to be x1k, x2k, so on up to xmk, and the received symbols are y1k, y2k, yrk. So, what we are saying is x1k x1k, x2k up to xmk, these are the symbols transmitted, these are the m symbols transmitted on the m transmit antennas at time k on the m antennas, or rather the m transmit antennas, and these, since you have m transmit antennas, you can transmit m symbols, and these I can write as the transmit vector x bar k equals x1k, x2k up to xmk. This is your m cross 1 vector, or this is the same as your m cross 1 input vector that we have seen previously. Okay. So, x1k, x2k, xmk are the m symbols transmitted from the m transmit antenna. Naturally, y1k, y2k, yrk are the r received symbols on the r receive antennas. Now, since we have multiple receive antennas, we will have multiple received symbols. Okay. So, what we have are y1k, y2k, yrk, these are R receive symbols on R antennas at time k, and the received vector y bar k, the received vector y bar k equals, this equals y1k, this is y1k, y2k, yrk, this is the received vector, and this is r cross 1 dimensional. So, we have an x bar k, which is the transmit vector, which is m dimensional, we have an r cross one vector y bar k, which is r dimensional, which is the received vector. Okay, correct. Now let us see how we can model the input output relation in the MIMO system. Input let us see how we can model the input output relation, and the input output relation can be modeled as follows. Let us look at y1 of k, symbol on receive antenna 1 at time instant k. This is given as x1 k h11 plus x2 k h21 plus so on x m k h m1 plus v1 k, correct. And what is y1 k? Y1 k is symbol on receive antenna 1 at time k, correct. Symbol on receive antenna 1 at time k. What is V1 k? V1 k is noise at receive antenna 1 at time k. Now look at this quantity H11, this is the coefficient between transmit antenna 1 and receive antenna 1. H21 coefficient between transmit antenna 2 and receive antenna 1, alright, and so on and so forth. So H11 coefficient between Tx1 Rx1, H21 this is the coefficient between Tx2 and Rx receive antenna 1. So Hji or Hij equals coefficient between Tx antenna I comma Rx Tx antenna I and Rx antenna j. Similarly, I can write Y2k symbol received on receive antenna 2, alright. Y2k is the symbol received on receive antenna 2 at time instant. Remember, we have R receive antennas, so at any point of time k we have R received symbols Y1k, Y2k up to YRK. So Y2k I can express it as x1k h12 plus x2k h22 plus so on plus x mk h2m plus v2k. Remember this y2k symbol on receive antenna 2 the symbol on receive antenna 2 at time, symbol on receive antenna 2 at time instant k, so on and so forth. I can extend this model to YRK equals x1k h1 r plus x2k h2r plus x mk HMR plus VRK, alright. YRK is the symbol received on receive antenna R at time instant k, alright. So now I have the relations for Y1k, Y2k up to YRK. I can now put these together as a vector, alright. So, now I can form the vector model as follows. So, I can write, and you can verify this, I can write Y1k, Y2k, YRK. I am writing this as a row vector, you can check this. This is basically y bar transpose of k, where y bar of k we have defined previously, that contains the r dimensional vector or received symbols at time instant k. This is y bar transpose k. This is equal to x1 k, x2 k, so on up to x m k. This is the transmit vector, which is x bar of k at time instant k, x bar transpose k, where x bar k is the transmit vector at time instant k, times the product h11, h12, so on to h1 r, h21, h22, so on up to h2r, hm1, hm2, so on up to HMR. This is your MIMO channel matrix H. And you can clearly see this is an M cross R. So, we have now the M cross R MIMO channel matrix H, correct, where M is the number of transmit antennas, R is the number of receive antennas, correct, and what is left is the noise vector, and the noise vector can be written as, so this is basically your matrix H plus the noise vector is V1k, V2k, so on up to Vrk. This is the noise vector V bar transpose of k, and therefore, a time instant, and this is also you can clearly see, this is obvious, you have R receive antennas. So, you have R noise sample. So, this is a 1 cross R vector, and therefore, what you have is y bar transpose k equals x bar transpose k times the MIMO channel matrix H plus V bar transpose k. Just to confirm this again, this is your 1 cross R received vector, this is 1 cross M transmit vector, this is M cross R MIMO channel matrix, this is 1 cross R vector noise vector V bar transpose k. Alright, so I have y bar transpose k equals x bar transpose k times MIMO channel matrix H plus V bar transpose k. This is the model input output model for kth time instant. This is the input output model for the kth time instant. Alright. Now, let us consider the transmission, or so this is for a particular time instant k. Now, let us consider transmission of n pilot vectors, that is, let us consider n transmission instants. Okay. So, let us consider the transmission of transmission of n pilot vectors. By the way, we have not mentioned it explicitly, but it should be clear to you that this x bar of k, this is nothing but a pilot vector. Since we are considering this for channel estimation, we are assuming this to be known, or rather we are going to be assuming this to be known, similar to your multi antenna downlink channel estimation scenario where you have the transmission of pilot symbols. Now we have the transmission of pilot vectors. Each x bar k is an m dimensional pilot. We have already seen this in the context of multi antenna downlink channel estimation, where each vector is a pilot vector, and that continues to be the case. Alright, x bar k is the pilot vector transmitted at time instant k. Okay, the input vector, or for the purpose of channel estimation, this is also we transmit known symbols, and these are known as pilot symbols. So, naturally we have a pilot vector. Alright, we consider the transmission of n pilot vectors. So, let these pilot vectors, let these n pilot vectors be x bar 1, x bar 2, so on up to x bar of n. These are the n pilot vectors, implies these correspond to the transmission of, well, k equals 1, 2 up to n transmission instants. These are the transmission instants. These are the n transmission instants, and let the n corresponding vectors, the received vectors, let the n corresponding received vectors be y bar 1, y bar 2 up to y bar n. Then what we have is basically the input output system model can now be formulated as, well, for every transmission instant we have y bar transpose 1 equals x bar transpose 1 h v bar transpose 1 y bar transpose 2 x bar transpose 2 h plus v bar transpose 2, so on, y bar transpose n equals x bar transpose n plus h plus v bar transpose n. Now I can stack all these as a matrix. This is your matrix Y, which has n rows, each of size r. So, this is n cross r, x bar transpose 1, x bar transpose 2 up to x bar transpose n. This is your pilot matrix, which is n cross m, MIMO channel matrix, which is m cross r, and we can stack this noise vectors as n rows, each row of dimension r. This is n cross r noise matrix. Therefore, stacking these as matrices, what we have, so stacking as matrices, or rather stacking as a matrix all the input output vectors corresponding to n time instants. We have y equals x times h plus n. You can contrast this with the multi antenna downlink channel estimation problem, where you have y bar equals x times h bar plus v bar, right, plus v bar. Now you have matrices. All right, let me just correct this noise matrix. This noise matrix we are going to call V, correct, naturally. So, this is your y x, this is your channel estimate, and this is your matrix. Let us call this noise matrix as V. Okay. So, this is your output matrix or your observation matrix or received matrix, which is your n cross R. This is your pilot matrix, which is which continues to be similar to the multi antenna channel estimation scenario pilot matrix, which is n cross m, where n is the number of pilot vectors, m is the number of transmit antennas. This is now a MIMO channel matrix. We have already seen this. This is now a MIMO channel matrix, which is m cross r. M is the number of transmit antennas, r is the number of receive antennas, and this is the noise matrix, which is basically your n cross r noise matrix, and therefore, this is your final MIMO input output system model. This is your input output system model for the MIMO channel, that is a multiple input multiple output wireless channel. So, let me just write that down also. This is the input output model for your MIMO, or basically multiple this is the input output model for your MIMO or multiple input multiple output wireless channel. Alright. So, this is the input output model for the multiple input multiple output wireless channel. Alright. So, what we have done in this module is basically we have developed this input output model for the MIMO wireless channel. There is a multiple input multiple output wireless channel considering m transmit antennas and considering n receive antennas, because you have multiple transmit antennas, multiple receive antennas, m transmit antennas and r receive antennas. Because we have multiple transmit antennas and multiple receive antennas, this becomes a multiple input multiple output wireless channel model. We have considered the transmission of n pilot vectors. We have first developed the input output system model for a single transmitted pilot vector, single received vector y bar, that is y bar transpose k equals x bar transpose k times the pilot MIMO channel matrix H plus V bar transpose k, where V bar is the noise vector at time instant k. Stacking all these, considering the transmission of n pilot vectors, stacking all these for n time instants, we develop the MIMO input output system model, where y the received the pilot matrix, the received matrix, the observation matrix y, which is n cross r, is equal to x, the pilot matrix n cross m, times H, the MIMO channel matrix m cross r, plus the noise matrix V, which is n cross r. Right. So, this is the MIMO model that we have set up. We are going to use this subsequently to carry out MIMO channel estimation, that is present the LMMSC or MMSC estimation of the MIMO channel matrix H. Alright. So, we will stop this module here and continue in the subsequent lectures. Thank you.